Anyway, welcome, wonderful people. Let's get started. So we're talking today, wrapping up chapter 4 of projectile motion is the name of the lesson. And we are going to apply strategies to solve quadratic word problems. Now, in this case, we're talking about something specific. I have shown you this slide before on where you can see parabolas in real life. And one of the examples I gave was a suspended chain will make the shape of a parabola under its own weight and structure. So that's kind of like a negative parabola, right? We have a minimum, you go down, reach the minimum, and then come back up. And same thing on here as well. Minimum goes down and comes back up. So they can be, they are parabolic shapes, but they can be different kinds. Over here is the one we're going to be talking about today, and that is specifically the path of projectile motion. So all thrown objects follow a predictable pattern of behavior. And I'm going to kind of do something a little bit different today, just because I have a few extra things. I was digging around my old stuff recently and dug this, I guess, toy up. You can see it on the little screen here. And that is a trebuchet, is the way it's pronounced. I just call it trebuchet. So what these are little models of medieval artillery, oftentimes used for knocking down castle walls. So how these work is that you have a counterweight right here. So that's full of heavy stuff, and it's pulling down on this side. So kind of like a seesaw, all right? When something is heavy on a seesaw, that's the side that goes down. The downward force pulls on the boom, which is this swinging arm, that pulls a sling that is released at a particular moment that lets go of the projectile. Can hurl a 90-kilogram stone ball up to 300 meters. So let's go ahead and give a little bit of an example of what that might look like. So let me go back here. Oopsie. To the main screen. And here you can see that I have mine ready to go. Okay, so let's go ahead and try. Well, this one here, I don't really have the counterweight is missing. So I don't really have the, it may or may not work the way I intend to, but I'm gonna go ahead and tap the trigger, and you'll notice that we're gonna have a downward and upward force. Here we go, 3, 2, 1. Oh, hey, what do you know? We got a little hit. Okay, but that one kind of bounced on the ground first. I probably need to get a better counterbalance on this one. Another one that you could probably also see is this little one down here. Oh, I don't know if you can see that one. Can you even see that? I'll show it in a minute. In the meanwhile, I'm going to go ahead and use our main piece here. And I'm going to go ahead and get ready to pull the trigger. So here we go in 3, 2, 1. Oh man, so close. Landed like right next to it, barely missed it. Maybe we'll try it again at some point. All right, so I got a little one down here that I did not show my first hour because it was off screen. Too bad. I was not well aware of the field of view on this. So I'm gonna go ahead and show you this one. I think when most people think of catapults, they usually think of something like this with a swinging arm held in by tension or torsion. So I'm gonna go ahead and tap the trigger. Okay, not the best, not particularly theatric. Oh well, it is what it is. Anyway, let's go ahead and get with the lesson today. All right, moving on with the lesson. Or actually, you know what? Let's see something get hit. So here are some examples of recreations that we have. You know, it's great. You see that little guy right there? The great thing about these is that there's really no limit to how big you can build them. Another one. And we have some actors in there. But let's see something. Okay, maybe you weren't ready for that. Let's start it from the beginning. Take that, piano. But again, notice the arc. It's not a semicircle. If you have somebody draw a cartoon, it's usually going to be in like a semicircle arc. But no, it's a parabola. I don't know if I have any more good videos on this. Probably not. But it gives you a little short article about it. In the meanwhile, let's go ahead and get back to the lesson today and talk about how we use the information we get from projectile motion. All right, so number one, a soccer ball is kicked from the ground with an initial upwards velocity of 90 feet per second. The equation h of t equals negative 16t squared plus 90t gives the height h. So h is height and t is time in seconds. So the way you would read this function, that's the word function, the height depends on the time, and this is our function, the equation part that tells us how far or where the projectile will be, in this case a soccer ball. How many seconds will it take the ball to reach its maximum height? Okay, so, thinking about maximums and minimums, let's see if I have a chart here. So let's go ahead and review something else that we may be familiar with, and that is graphing. All right, so we've graphed it. This is our graphing tool that we've used. And here we have a parabola. And what we're looking for is the maximum. Now, this is not the graph that we're looking at in our problem. So this is a completely different problem. So we're going to have to find out this one in another way. So again, we're looking for the maximum height. So when an object is launched, it kind of goes in the air and comes back down. Let me make that a little bit more parabolic. Kind of looks like that. Although it would continue downward, but we don't really need to worry too much about that because the ground, it starts from the ground and ends on the ground. Because this is a soccer ball, so I'm guessing it's on a soccer field. So what we need is the axis of symmetry. And that formula for the axis of symmetry is negative b over 2a. Negative b over 2a. And let's go ahead and start plugging in some of our numbers. In this case, we need our standard form, which is ax squared plus bx plus c. So that is the standard form, which in this case here, we do not have a full out standard form because, well, we don't have a c value, right? We have a t square and a t, well, actually it'd be x. If we were to graph this, we would need to replace t with x because x is the sideways, but in this case here, x is t. And if we're talking about graphing it, y is the height. So negative b, so that would be negative 90 over 2 times negative 16. All right, so that would be negative 90 over negative 32. Now in this lesson, I'm going to be using a lot of calculator because we are we are working with a lot of very precise decimals. So I'm going to go ahead and move over to the calculator, and remember that it's negative 90 divided by negative 32. So a negative divided by a negative is going to be positive. So I'm going to ignore the negative, which in this case, I'm going to have to do this quite a lot because, well, we don't really have all of those going on. This calculator will not allow me to write numbers as negatives. It will for the first number, but after that, it usually won't. Okay, so anyway, so our number is 2.8125. 2.8125. Now, in reality, you would not be able to perceive the difference between 2.8 seconds or 3 seconds. All right, you would need really fast reflexes or a very good sense of time in order to figure that out. But here we have the axis of symmetry. And if you remember, the axis of symmetry is that line. Okay, now excuse my kind of not very good drawing, but it would be this line. And this is not really, well, actually, this is the answer to the first question. How many seconds will it take for the ball to reach its maximum height? And remember, x is time. So in this case here, we have 2.8125 seconds. And I'm going to just put SEC for abbreviation of seconds. There we go. But we need this to answer the second question. And that question is, what is the maximum height of the ball? So how can we figure out how high this ball went? Well, we know when it reached the maximum height. So what we're going to do is we're going to take this and plug it back into the original. So plug it in. So negative 16 t squared, which is 2.8125 squared minus, actually in this case I need plus here, 90 times t. And again, t is time in seconds. And what I'm doing by plugging in 2.8, I'm not going to say the whole number every single time, but this 2.8 number, by plugging it into the equation, I'm asking the function, where is the ball in 2.8 seconds? That's what I'm doing. Okay, so let's go ahead and go back to our calculator, because in this case here, again, we are looking at very precise values. So we have 2.8125, and I'm going to square it using the square button. So I get 7.91 number, and again, I'm going to not say this every single time, and times that by 16, and you get this number here. Now, okay, so let me go ahead and go back to the other screen. And I have, let's see, 126.5625. All right, now in this case here, again, I mentioned my calculator is not able to calculate negatives. So I have to be the one to keep track of the negatives, not the calculator. So there you go, we put that number in there, and now I'm gonna see what 90 times the 2.8 number. So let's go ahead and do that, 2.8125 times, and the number we had was 90 from the formula. So this would be 253 1/8. Oh no. All right, so, and I'm gonna go ahead and multiply, I'm sorry, not multiply, but put these two numbers back together. So I need to subtract this from that. So go back to the calculator, and sometimes I'm not always gonna go straight back to the calculator, but we're gonna take this number and minus the other number we had, which was 126.5625. 5625, and we should be able, okay, it might be a mistake because, well, I don't know. Okay, so we got this 126.5625 number, but maybe I pushed the wrong button. Let's square it and see if we get the same thing, or not square it, I should say double it. So I'm gonna times it by 2, and it turns out that actually it is exactly halfway. So it seems like we made a mistake, but we didn't. So this number is half of this number, which means that the maximum height, and since this is positive and the positive number is bigger, that's going to make our height positive, which makes sense. Okay, our height should be positive. And in this case here, we're talking with feet. So this would be feet per second is the velocity. So if we were measuring the height, it would be in feet. So we have 126, roughly 126 feet and half a foot, which is about 6 inches, a little bit longer than 6 inches, maybe like, I don't know. We probably don't need to be that precise about it. Like I said, if you were looking at this, most people who were able to calculate the height would just say 126 feet, or maybe they might even round it to 127. Or if they were trying to be precise, they could say 126 and a half feet. Okay, but this is accurate enough. So let's go ahead and move on to the last portion of this problem, and we are going to give the domain and range. So domain, and remember that domain means the x values. So the x values are these numbers from here to here. So again, domain is x values, so x is time. So you have 0 time, and the time when the ball came back down. That is the time the ball was in the air. So let's see, our t or x, in this case here, let's go ahead and use x. X, I don't know what happened there. My keyboard went out. But x has to be less than, that's a good question. So I'm going to double this number here, the 2.8, and I'm going to go ahead and double that really quick. And we get 5.625 seconds. That is the time, 5.6 seconds is the time that the ball comes back down and it impacts the ground. But we also have another time that we have to keep in mind, and that is the time of 0. So in this case here, it would be from when the ball was first kicked. So between 0 and 5.6 seconds, that is when the ball was on the ground. Now in this case here, if you forgot to put these in there, I wouldn't blame you, but it's supposed to be or equal to numbers. Okay. But again, if you missed that, that's fine. I'm not going to be hard on that. So let's go ahead and find the range. So the range are the difference in y values. So how high and how low did the ball go? Well, the ball started out on the ground, so we must include 0. And the y, or the height, was between 0 and the maximum height, which is 126.5625 feet. So there we go. We have our domain and range calculated now. And there you go. There's question number 1. Now, I know you're probably thinking that this is going to be a pretty long assignment, which it probably will be. I think for most of my other classes, it was actually a pretty long class, a little bit longer than usual. It's a little bit over the time I have. Maybe it had to do with the intro. But I'm going to go ahead and continue. But most of these are just going to be one question. So in that first example, we had to answer 3 questions. I think with most of these, we're only going to have to deal with 1 question. All right, so here we have another one. An apple is launched upwards at 64 feet per second from a platform 80 feet high. All right, so as I was mentioning, word problems have several parts. every word problem has exposition, and then they have what I call clue statements, and then they have a question. So these are the three things that word problems have. Exposition tells you what's going on, just like in a story. The story in an old book might read something like "long ago in a kingdom far away," right? Or the first sentence of a science fiction book may be "on a planet at the edge of the galaxy, there was blank." Okay, so that tells us what's going on. So in this case, we're launching an apple from a platform that is 80 feet tall. And we have a person here, and he's launching this apple upwards at 64 feet per second. And it gives us the equation. And we have the same sort of equation. We have h and t for height and time. And here they give us the equation. Now, those are the clues. And the question is this last part here. What is the height of the apple after 3 seconds? All right, so which of these pieces of information are useful? So this here, so let me go ahead and explain what each of these parts are, because it is going to be helpful later. Oopsie. So this first number here is gravity. All objects on Earth fall at negative 16 feet. So they drop 16 feet every second squared. Okay. So in 1 second, something will fall 16 feet. Now, it's not going to stay constant because, as you know, the higher something falls or the longer that something falls for, the faster it's going, which is why if you fall off a chair, it's not really going to hurt. But if you fall off a ladder, that's probably going to hurt more. And falling off a building hurts even more. So the higher up you are, the faster you fall. So that's why the time is squared. And this part here is velocity. That is how much force you are putting on the object. And velocity is, again, is the force. So if you remember the two models that I had, one of them was not particularly strong and the other was able to fling the object further along, it would have hit if I was just a little to the right. But again, you could obviously kind of tell if you were paying attention that one is stronger than the other. And this is height. Wait a minute, that doesn't look right. Oh, it is right, okay. Oh yeah, right there, I can see it. So, but more specifically, it is the starting height. So in this case, it makes more sense. If you throw something off of a building, it will spend more time falling and it will be higher with the same amount of force. All right, so again, the ground is 0. So let's go ahead and calculate this out. So how do we figure out the height of the apple after 3 seconds? So this function is telling us height in relation to time is this formula. So height of time is the way you would read that. So what we're going to do is we're going to plug in 3 seconds. So negative 16. So what I'm going to do again is I'm plugging this in because I am asking where is the apple? Sorry. What is the height of the apple after t is 3 seconds? So in 3 seconds, where's the apple? Okay, that's what I'm asking. So by plugging it in and evaluating it, we should be able to get this pretty easily. So negative 16 times 9 plus, and 64 times 3, what is 64 times 3? That would be, okay, let me just, 192, use my calculator, plus 80. Now I'm going to go ahead and put this together. So 16 times 9, that's going to be 144. So negative 144. And I'm going to go ahead and add 192 and regular 80, I should say. That'd be plus 272. And I'm going to go ahead and minus 144. So we get 128. So h, right here, still h, the height is equal to 128 feet. So at the vertex right here, so in 3 seconds, it has gone up 128 feet. So that's kind of the way you would calculate that. And if we wanted to know when the ball hit the apple hit the ground, we would need a different set of problems. So in this case here, this is just here to help us. It's really just here to help us, figure out the problem. But you will need different things for different problems. But remembering all the pieces is really going to help. So this chapter here brings together everything we've learned about parabolas and quadratics. Okay, it's time to apply everything. Okay, here we go. Next problem. A toy rocket is launched vertically upwards from a 12-foot platform with an initial velocity of 128 feet per second. Its height, h, and time in seconds, t, after launch is given by this equation. How long will it take the rocket to reach the ground? So we have a little platform. Okay, it's 12 feet, which is why this number is 12. And an upwards velocity of 128. So there we go. Middle number is 128. And then we have our gravity, which is constant. Gravity does not change, okay? If no matter where on Earth you go and fall off or throw something off, it's usually going to be about the same. So there we go. A toy rocket goes up and comes down. So we end up with a shape like a parabola. But how do we figure out how long it would take to hit the ground? Well, the ground is 0 feet. So what we're going to do is we are going to, so h equals 0. So ground is h0. Right? So what we're going to do is I'm going to plug in 0 equals negative 16 t squared plus 128 t plus 12. So there you go. I'm now, by plugging h as 0 into the formula, I'm saying, what is the time when h is 0? Okay, so again, you got to kind of take the clues that you have and plug it in. So if you remember yesterday, we were talking about strategies for solving problems. And some of these, let me see, we go back here. And we were talking about familiarize. Okay, so set it up. Draw a picture, diagram, graph it if you can. Make a list of what you are trying to find and a list of what you have. Look for the clues. Estimate to get an idea, and if possible, look for keywords, which actually in this case, there aren't very many keywords. So those are all the steps that you would use for familiarizing. Translate means to assign values and variables. So in this case here, we're using quadratic formulas. Well, okay, so for this example, we are going to use the quadratic formula, but solve, check, and state answer in given units. So same things that we did in the previous lesson. Okay, so let's go ahead and solve this. So if you remember, I was talking about solving quadratics, and I kind of said that there are some ways you can do this. So probably the easiest way, thinking about it yesterday, the first thing you should try is use the square root property. If you can't do that, you should try to factor it. If you cannot factor it, you could try completing the square. And last option, if all others fail, there is what I call the big hammer, right? The big hammer is what you break out when everything else doesn't seem to be working. In this case, it's the quadratic formula. So these are the steps that you should take in that order if you can, okay? Now, if we try to use square root property, it's not going to work with this one because we have a b value. Square root property works best when you do not have a b value. Now, you could try to factor it, but in this case, it's not going to factor well because my c value is very small compared to my middle number. And if we try to use the double bubble, or as I call it, the LOIF method that we've been using, it's not going to work. We could try using the AC method, but we would be guessing a lot. Also, if you look at some of the other problems that we've been doing, we have big decimal numbers. So because we have a high chance of having big decimal numbers or numbers with lots of decimals, it might be a safe bet to use the quadratic formula. Now, again, quadratic formula is a little bit tough to remember, but it's negative b plus and minus b squared minus 4ac all over 2a. And again, that's a little bit to remember, but it's worth it if you need it in a case like this. We do need it. So let's go ahead and put in negative b, which is a negative 128 plus and minus the square root of b squared. So let's go ahead and take 128 and square it, minus 4 times a, our a value is here, and c. Now we've worked with quadratic formula in the past quite a bit. So I'm going to kind of, I'm going to try to get through this a little bit quicker. I'm trying to be cognizant of the time because I don't want to be taking too long. So I'm going to go ahead and use my calculator, 128 squared. And let's see, if, okay, so that's going to be, all right, I got that. Now let's go ahead and negative 4 times negative 16. So negative times negative is going to be positive. So that's going to be 4 times 16 times 12. I'm going to add those together here. And we get, well, all right, so that's our discriminant. That's what it's called. It's called our discriminant. And I'm going to put this all together and we get 17,152 all over negative 32. All right, and from here we would break it into two possible answers. Now, if I take the square root of 17,152, so I'm going to need the square root button, which is this one here with the radical. And I'm not sure what kind of calculator you have, but it would pretty much be the same symbol. So we have 130.965, and then we have a whole bunch of other numbers after that. But we're going to round it off to 3 decimal places. So I'm going to go ahead and go back to this thing here. And it looks like I'm running out of space already. So I'm going to go ahead and just kind of get that out of here. So 130.966. So again, I rounded that last number off. And let's see, if I have a negative divided, so negative and negative make a bigger negative, divide that by a negative, we get a positive number. So that might be a clue on what we're trying to get. However, if I take this number and I add this number, I would get a very small number. So this is 130 minus 128. That is a tiny number. We would actually get not 0, but we would get 0.093. And if I did it the other way, so negative combined with a negative is a bigger negative number on top. Negative divided by negative is positive. So in this case here, I would get 8.9, or hold on, 8.093. And that would be a positive number. But remember, like we were talking about yesterday, does it make sense? Do either of our answers make sense? And again, I call this the sniff test. You're not sure if that shirt you have is clean enough to wear again for the 3rd day in a row? give it the sniff test. In this case, this one fails the sniff test. You cannot have negative time. Okay, you cannot have negative time. But you can have positive time. So in this case here, I think we have our answer in this case. And that would be 8.093 seconds. Now remember, both of these are answers, but this one is the solution. So I know yesterday we were talking about solutions versus answers. So I always get students that confuse those two things together. They think if it's an answer, it must be a solution, but that's not always the case, because the answer is basically what you are looking for. We have answered this question. The solution is what you plug back in to the original or into the model to make it work. So there we go. Let's go ahead and move on. Let's keep things moving a little bit. Like I said, we got quite a bit to cover. I think we have about 9 problems. We're 1/3 of the way there, and we've spent about 30 minutes on this lesson so far. So let's keep things moving. Ooh, I like this one. There's a myth behind this one. I'm pretty sure you've heard this one. And that is, the myth is that if you throw a penny off of the Empire State Building, it will severely hurt or damage, maybe even unalive somebody if it lands on them on the floor. Or they would say like a penny falling off the Empire State Building would damage the concrete or crack the concrete. But that's not really that true, actually. That's kind of a myth. Well, in reality, the penny would only fall until it reached terminal velocity. Once it reaches terminal velocity, it will stop falling faster, and it will fall at a constant speed because the air's in a way kind of pushing it back up. The other thing is that the wind focuses off of the buildings, because New York City has not just one building, but many buildings. And depending on which way the wind is blowing, sometimes you can actually get things blowing back up onto the balcony. So it's probably realistically going to take a little bit longer than that. And a penny is a bad one because it is flat, and depending on which way it's falling, it can divert the air. Anyway, back to the problem here. So we have the Empire State Building, and we are on the top floor throwing pennies off. So there's your little arm. Now in this case, there is no upwards velocity. So since there is no upwards velocity, remember we were talking about that on one of the previous ones, that this is the upwards velocity, the middle number. Yeah, this one doesn't have that. So this means that the penny is not being thrown, it is being kind of dropped. So just from dropping it, how long does it take to reach the ground? So again, starting at 1,250 feet, it's going to be falling 16 feet every second squared. Okay, so how long would it take for the penny to impact a 6-foot tall person? So we have a poor, hapless pedestrian on the ground. I don't know. Anyway, so how long would it take that penny to strike him? Okay, so what we got to do is let's go ahead and start with our equation. So negative 16t squared plus 1250. Now, looking back at our methods, right? Because we have various methods available to us. Square root property is the first one. So this one is a very good candidate for square root property because it does not have a b value. And I say that because square root property is closest to what we normally do for algebra. Like when you add, subtract, multiply, divide both sides using your inverse property, basically what you've been doing since 7th grade. That makes a little bit more sense. Now I'm also going to switch sides using the reflexive property. So we cancel this number here. So 16t squared equals 1,250. So there you go. I just switched the sides that each number is on. So I want to put the variable on this side because that's the way it's mostly done. So divide both sides by 16. So that leaves me with t squared equals, oh shoot, you know what? I almost forgot something. In this case, the penny actually has a shorter path to fall. Because the guy is a little bit taller, that means the penny will strike him before it strikes the ground. So that means that it has a little bit less path to cover. So let me go ahead and, oh wait, hold on. Before I go back over there, let me show you what we're gonna be doing with this. So I'm gonna go ahead and, oh wait, now I remember. I was gonna divide this by 16. So we end up with 77.75. Now it's called the square root property because to get rid of this 2 power or the square, I am going to take the square root of both sides. So by taking the square root of both sides, all right, and again, I already did this off screen. Let's go ahead and take the square root of that and let's see what we get. So we get this number 8.82. I'm going to round it to 2 decimal places. I don't know if that's, it doesn't, the question does not tell us where to round it. Oopsie, we got rid of that square. So we got rid of the square root and square is inverse operations. They are inverse operations, so they will be undoing each other. So the time in flight while it's falling, the time of falling is about 8.82 seconds. Now, if you were timing this, if you were watching this penny fall down, you would probably say it's about 9 seconds. You would probably not be able to perceive with your own mind without a stopwatch. Or maybe if you had a stopwatch, then you could get 8.82 seconds. Now, this is a little bit unrealistic because we completely ignore air resistance. Air, like I said, the air is going to kind of slow the fall a little bit. So in reality, it might be 9 or possibly even 10 seconds. But anyway, that is it for that one. And there we go. It would take 8.28 seconds to strike somebody. Hopefully they have a helmet on. I don't think it would be that bad, actually. I think it would probably feel like the penny was dropped only a few feet above them, actually. I don't think it would really hurt them. I think it would just, you know, at mildly, it kind of just feels like a penny being dropped on your head. It's not going to be gaining more and more velocity as it falls. All right, now this next question I have a bit of a problem with because here it says fireworks fired vertically in the air, right, at 80 feet per second upwards. The object's height and time is modeled by this equation. Find the domain of the function. And I don't really like this because in the domain, okay, so remember domain is up and then down. So domain is time from launch to time recovered on the ground. But this one is kind of not a very good example because anyone who's ever seen fireworks would know that a firework goes up and then bursts. Hey, that's not bad. And it does not come back down. Or if you've ever managed to spot pieces of it coming back down, they're usually very light pieces of cardboard that fall very slowly. So this is a very bad equation because again, most fireworks will blow up. But let's say that this is a dud firework, okay? Or maybe it's not an exploding firework. Maybe it's like a rocket, or I don't know, maybe it's like a rocket that goes up and shoots sparklers on the way down or something, who knows? Or like I said, let's just pretend it's a dud. Let's just pretend that the main charge has never been set off by the thrusters. Okay, so anyway, let's get back to the question. So 80 feet per second, so there we go. That's why the 80 is there. And we have negative 16t, so we want to find the domain of the function. So what we need are the zeros. And again, they are zeros because the ground is 0 height. So to find the zeros, we're going to need to solve this for 0. So I'm going to set h equal to 0. By setting h equal to 0, I'm saying, when was the rocket on the ground? Well, it's fired, so I'm guessing it's a bottle rocket or something like that. So when did it reach the ground, and when was it, basically, when was it on the ground? So if we look at the chart, I should really put this chart on all the pages. So we cannot use square root property because we have a b value. So we could try to factor it. And if you look at the previous lessons, factoring it is probably one of the best ways to do this. So let's go ahead and factor this. Now, there is a better way to factor this because we do not have a c value. We can skip using double bubble, and we can use what's called the reverse distributive. So you're all familiar with distributive property, right? With distributive, you give something like Santa Claus. However, we are taking stuff. We are dividing both numbers. So I want to take the biggest number that I can divide out of both of these numbers, which in our case is 16, because 80 and 16 can both be divided by 16. Now here's a bit of a weird thing, because we are going to take the negative out as well. Now you could do this, but you would get one of your times to be negative, and we cannot have negative time. So that is one of the other strategies, is to check it. Does it make sense? Plug it back in. So if we did not take out the negative, we would have had like a negative time, which since this started and ended on the ground, it doesn't make sense. We also see that both of these numbers have a t. So we are going to take out a t from both of these numbers. So I have t, because this first number here, we took the 16, we took its negative, and we took one of its t's. So it's only left with 1t. Now for this next one here, 16 divided into 80 is about 5 times. Using our zero product property, I'm going to make 2 equations. So negative 16t equals 0, and t minus 5 equals 0. Let's just solve it. So I shouldn't have to tell you this, but if you need to multiply something by negative 16 to get 0, well, there's only one possible thing that it can be, and that is 0. Or 0 divided by negative 16 is 0. What, don't believe me? 0 divided by 16 is 0. So there we go. That is one solution, maybe. And here I would have to add 5 to both sides. And that would give me a second possible solution. But again, we have to check it, make sure it works out. Give it the old sniff test. So at 0 seconds and 5 seconds, the rocket was on the ground. That makes sense. So the domain, that means when the rocket was launched. The rocket was in the air in 0 seconds. After 0 seconds, I should say. So if x was like, let's just make up a number. Let's say 3 seconds. Yeah, the rocket was in the air after 3 seconds. But it came back down, right? It touched down back on Earth at 5 seconds. So at 5 seconds, it was back on Earth. And we are done with this one. We have answered the question. We have found the domain. The time is, the time of the rocket being off the ground was between 0 and 5 seconds. So this one was a pretty easy one, I guess. Not a very particularly difficult problem. Sorry, I still have some trouble speaking sometimes. It should be back to normal next week is what I'm guessing. So hopefully we can start doing videos the way we used to next week, hopefully. Still got some numbness in my tongue, and I don't know if I'm ready to give a full face thingy again. All right, number 6. The Apollo Chariot, which is a roller coaster at Busch Gardens. So there's our exposition. It is explained to us what's going on. There's a roller coaster. And here's the clue statement. Moves at 101 feet per second. And again, we use h for height and t for seconds. And we represent it with this equation. And again, there's the gravity force again. Plus 101 velocity in seconds. Plus 10. So what is the maximum height reached by the ride? Okay, now we're going to have to do the same thing. So I'm guessing this roller coaster probably does something like that. I'm guessing. I don't know. Actually, most roller coasters are not actually powered. They actually just sort of roll to the bottom. So if you know most roller coasters, if you've ever ridden one, you notice that when you start it goes like chugga 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 chugga, kind of like pulls up, kind of. There's that ratcheting mechanism that slowly pulls it up. Then it falls and it makes all these loops and rounds and turns, right? So those are all. That's all just gravity. I think very few roller coasters are actually self-powered. They might have some kind of assist device on them. Because I've heard of roller coasters getting stuck, and I'm guessing they do that because they run out of force at some point, or perhaps something slowed it down on the tracks. Anyway, sorry, getting off subject. Maximum height. So this, we need this formula. We need the vertex, or in this case, axis of symmetry. But we are actually going to need to find out what is the axis of symmetry. So negative b. So negative 101 over 2 times negative 16. And let me go ahead and start evaluating this. So this would be negative 32. So don't forget that a negative divided by a negative is supposed to be a positive. So I'm going to go ahead and ignore the negative. So 101 divided by 32. So we get this really weird number, 3.15625. Let's get back to the assignment here. So in this case here, axis of symmetry equals, or in this case here, let's go ahead and say that this is the max height. Or actually, you know what? I don't even know what this roller coaster looks like. It could be like the Batman, or no. What is it called? Was it Batman or Superman Escape? I think it's the Superman Escape at Six Flags. That one just goes up and then you roll back downwards. But actually that would follow a parabolic path in terms of time, not necessarily an actual path. But let's go ahead and put that number here, 3.15625. Now I'm gonna need to plug that back in here because I know when it was at the maximum, but I don't know what the maximum height is. We don't know the height. We know when it was at the highest. So now I need to ask the function, where was the roller coaster at 3.15625 seconds? Negative 16 point, oh wait, we don't need t. We're gonna need this thing here, the number that we just have. And I don't wanna be saying this number every single time I write it, because then that would just take too long. And in my case, it would be tiring for me to say that every single time. Okay, so let's go ahead and I'm going to use my calculator and we're going to calculate this. Oopsie, sorry. Looked like it accidentally went off screen. Oops. Okay, so there we go. I got it. And all I did was square this, times it by that. And it's not really anything that's vastly different, okay? It's not really, I'm not really doing anything we don't normally do. Okay, I just multiplied and then did some adding. I was like, square this, multiply it to that, multiply it to this, add it to that, and then subtract this from those, and we're pretty much done. Oopsie. Where did I get that from? Sorry, I'm probably just still on the last. Oh wait, no. What am I talking about? Okay, sorry, I'm just. All right, sorry, looking at the wrong screen. All right, there we go. So 169.391 feet. Now I'm actually kind of curious about this particular roller coaster. So I'm going to go ahead and go a little bit off topic. And if you've ever been in my class, sometimes I do this as well, because I'm just curious about this myself. Apollo Chariot Busch Gardens. Come on, let's look at what it looks like. Oh, okay, so it is kind of a parabola shape thing. And it talks a lot about it, but it doesn't give me a big image of what it looks like. Let's look at some pictures of it. Okay, that's a little bit more telling. And it looks like it does have that arch. Okay, so there we go. At least I'm not giving you bad information. And I don't know, we could have checked the height. I guess it was on the Wikipedia page. Ah, sorry, gotta keep moving. All right, we got two more after this. Ava is jumping on a trampoline. Her height h at time t can be modeled by the equation here. Would Ava reach a height of 14 feet? Now there are two ways that I would suspect that this could be done. The first way is to plug in 14 for h and see if we can get a true statement. But the other way we could do this would be to find the axis of symmetry and plug it back in and see if it works. So you'd pretty much do the exact same thing we did on the previous problem. And let's see, that would be something like this. Let's see, negative 20 over negative 32. So that would be 0.625. There you go. So now we know when she was at her max. So we know the time that she was at her max jump height. What we're going to do is plug this back into the original and see if it works out. So 0.625 squared plus 20 in time. So I'm basically asking, okay, so where was she at 0.625 seconds? So I'm going to plug this back in and we're going to go ahead and work this one out. And this one is going to be 12 seconds, 12 and a quarter seconds. Oh, wait, no, I'm sorry. In a little bit over half a second, her max height is 12 feet, 4 inches, or 12.25, or the quarter, you know, it's 1/4, 1/4, which again, in terms of feet is going to be 12 feet, 4 inches is her max height. So did she reach a height of 14 feet? So again, we got to make sure to answer the question. We got to make sure the question is answered. In this case, the answer is no, but the solution is 12.25, because this is what you would plug back in to make it work. Sometimes you need solutions, sometimes you need answers. But again, that's the part on you that you got to figure out. So she never jumps more than 14 feet. Okay. All right, here we go. A diver is standing on a platform that is 25 feet above the pool. I'm guessing it's a diving board. Just by the way this question reads, I kind of feel like it's a diving board. So 25 feet above the pool. He jumps from a platform with an initial velocity, so he is jumping upwards at 10 feet per second. Now, jumping up 10 feet per second, that is really significant. I would imagine that if I told you to jump, you would only jump about 3 feet in the air max. And that is picking up your feet. Okay, to jump 10 feet a second into the air, you got to be like, you know, Olympic high jump champion or something like that. So I'm guessing by the way this is written, he's probably jumping off of a diving board, because a diving board would give a spring assist to his jump. Okay, but that's not really important right now. Use the formula. Again, this is gravity, velocity, and height, starting height. So that's why it says S there. And it gives us the stuff we already know. Velocity, time is the starting height. Write an equation to model the dive. Okay, so, well, we account for gravity. We account for his velocity, which is 10 feet a second. 10 feet per second. And he starts above the ground, above the water, the surface of the water, 25 feet. So that was actually a very easy kind of question. And it's a good thing because I did talk about this earlier. So I didn't have to explain so much when we got to this last slide. Find the diver's height after 2 seconds. So it's probably around here somewhere. He could be a little bit higher than 25, or maybe a little bit lower. Who knows? Maybe after 2 seconds, he's starting the downward drop. So let's go ahead and plug this in. And while I'm at it, I should have just cut and pasted this here. In fact, you know, it's not too late, because I feel like I'm going to save a little bit of time plugging it in. So in 2 seconds, and I'm going to just replace all the t's with 2. There we go. So 2 squared is 4. 4 times negative 16 is negative 64. Plus 20 plus 25. And 20 plus 25 is 45. So it's negative 64 plus 45. Wait, hold on a minute. You know what? Maybe I made a mistake. 16 times 4. I said 16 times 4. Okay, I feel a little bit lost on this one here. Let's, I'm going to use Desmos for this one here. In fact, actually, I used Desmos for some of them in my first hour. I was showing some of the things. Oopsie. So I'm going to go ahead and just plot it in, because somehow this one feels wrong. And when I worked on it this morning, I actually noticed that something just didn't seem to add up. So I'm going to go ahead and plug it in, plus 10x, and I'm going to replace x with t with x, so that it can graph. So here we can see his path, right? He began 25 feet in the air. And I want to know where he was at 2 seconds. So when x equals 2, where was he? There we go. So in 2 seconds, he was actually below the surface of the water. Now this is assuming that he kept falling through the water, okay? But if you know anything about landing on water, usually once you hit water, you start to slow down. So again, this one didn't really make sense to me at first. I was kind of like, really? Is that really what's going on? But again, once he impacted the water, he was underwater. Maybe I should make this look more like water. Ah. So there you go. H equals negative 19. And there we go. That's gonna be it for today. I'll go ahead and get ready to sign off on this one here. So don't forget, if you like the lesson, give me a thumbs up, share this video with your friends. Make sure you hit that like, share, and subscribe button. And I will see you guys later.